Welcome back to class 12. Here is example 316 from our textbook. A 25 kilogram cast iron wood burning stove, shown in figure 328, contains 5 kilograms of soft pine wood of 1 kilogram and 1 kilogram of air. I don't know how they know that, but it's okay. All the masses are at room temperature, 20 degrees Celsius, and pressure, 101 kilopascals. The wood now burns and heats all the mass uniformly, releasing 1,500 watts. I don't know how they know that either. Neglect any airflow and changes in mass and heat losses. Find the rate of change of the temperature and estimate the time it will take to reach a temperature of 75 degrees Celsius. Okay, well, I'll say right away that this is probably not a problem that will be on, I don't know, I haven't written homework yet, so I can't 100% say that, but it's not something that I'm going to emphasize terribly on. It's also sort of a weird problem on one level because there's so much more going on in a wood burning stove than this. But somehow, it's, I guess, an example of a transient thing, so more power to you. So writing down the information given to me: 5 kilograms of wood, 1 kilogram of air. Take a lot of air to make 1 kilogram. Things that they said. Okay, so we get the outside world is 20 degrees Celsius. This this thing starts out at 25 degrees. What I wrote there, I wrote that he was 25 kilograms. Let me write down there. The iron mass of the iron was 25 kilograms. There's a lot of it. And the outside world is 101 kilopascals, regular ambient, good old-fashioned temperature. All right. Oh, and the heat transfer rate. So it's going to be a rate because it's in watts. All right. Between 1 and 2, it's going to be 1,500 watts. And we're trying to find the rate of change of temperature. So this is dB, dt, 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 dt. So if you were looking at this, we would find the internal energy of this thing at any given time is going to be the mass of, let's say, the air times that rate of the air. Not rate of the air, that I'm trying to think. The internal energy per mass plus mass of the wood, the internal energy of the wood, and then the mass of the iron, and the internal energy of the iron. So if you take a rate of it, we'll use this. So the rate. Let me go ahead. I'm not going to rewrite it out again. Rate is all this because the masses don't change right here, so all those are going to be equal to it. And so what you're really looking at here is you're going to have each of these we can replace with the CV dt d little t, and this is going to be of air, and this is going to be of wood. But by the way, wood doesn't change volume much, so we usually don't put that V in there. I think they might do in the back of the book, tell you shit, now that I think about it. But it says in the book that you usually just leave it out. And I think in the examples, they just leave it out. So here's the iron, dt, dt. And so you can see all of those together. We can lump them all together. Write out the first law. You have U dot is equal to Q dot minus W dot. There's no work going on right here. So these equal to each other. So what we're going to be able to find is dt dt is a rate. It's going to be that Q divided by M air CV air plus M wood, CV wood, plus M iron, CV iron. Okay. Given. Look it up. So let's look it up. We're gonna find these. And right here for air, right? It's 0.717. I already had it highlighted. There you go. Highlight it again. All right. So that was table A5 and table A6. That's not gonna help us any. Right here, table A3 and A4. We don't need liquids. Let's go over here. Look, they give us pine. 1.38. See, they say CP here, but don't worry about it. Their pressure's basically constant, so whatever. They also give us iron. They give us iron somewhere. Where's iron? Metals. Iron. Ooh, we got two. Let's go with this one. This also says stainless in there. It's the 304 stainless steel. Hard to say. This just says cast iron. Does this thing say cast iron? It says a cast iron. Yeah. So we got it. 0.42, 1.38, and one third direction. 0.717. So let's write it out. So up here we got 1,500. And what are these guys? These guys are joules per second. Boom. And this mass of air is going to be 1 kilogram times 0.717. And these are kilojoules, is that right? Yeah, I think they are. Let's double check that. Units wars. Ooh, kilojoules. Ooh. What do you say we make that? Make that kilojoules. So it works out. Kilojoules per kilogram degree Kelvin. So that's on the bottom of the bottom, so it's going to come back up on top. So those are going to go away, and that's going to go away with that, right? So what we're going to end up with is kilojoules per second. That's what we wanted, right? dt, kilojoule, not kilojoules, excuse me, degrees Kelvin per second. So we got Kelvin per second, so that these make sense. Can't talk. And I can't remember this. This is 5, right? 5 of wood. Yes, 5 of wood. 5 wood. Give me 5 wood. 1.38 and plus 25 kilograms, and this was a 0.42. And what we found for our dt, what units did I use? Oh man, I don't know if I got the right units. Should we pause for a second and find out? No, let's just do it. This would be the correct one. We took 1.5 and did 0.717 1.38 times plus 25.42 times plus, and then divided. Yeah, okay, I got it right. I could just trust myself, right? Just show a little trust. Degrees Kelvin per second is what we're saying the rate is going to be of heat. All right, it's probably going to be an average though, because we just saw in the previous graphs of this thing, right, when we went to this, we saw that, you know, transfer doesn't always happen in a linear fashion. So that's sort of like the slope, by the way, that thing that they were being asked for. So I don't know. It's a sort of a linear assumption that that's the rate. The rate doesn't have to be constant, but they're kind of giving us saying it's assuming it's constant. They also want to find out what the final temperature is going to be. So this is basically all you need to do is kind of think through. Uh, I don't even know where they might have got this from, but it just makes logical sense that you could integrate this thing, dt times dt right there, and you can integrate this, like treat that as a value right into the thing, and then once you were to integrate this, you would take, if you said that this was constant, right? So let's go assume constant, that you would integrate, and so you would just get that number dt times a delta t, right, against that time. So you could find out how much time it took. So delta T is just going to be equal to the change in temperature divided by this rate that we just found. Right, so they said that the changes, they want to go to, how long will it take to go 75 degrees? So 75 minus, it started out at 20 degrees. Here's my delta T. And we divide it by 0.0828 degree Kelvin per second. And you get 664 seconds, which turns out to be 11 minutes. They probably rounded off. But you know, this is a good case where you don't want to use a lot of sig figs, because somebody might take a stopwatch out and measure, and you go, oh, you said 11.1 seconds, and it's 11.2 seconds or minutes. You're like, well, I'm just impressed that it's in the ballpark of the prediction of the temperature. So this, once again, as I alluded to in the previous video, discussing the topic of section 3.13. When this is heat transfer stuff, or similar to heat transfer stuff, and not necessarily things that you will be doing further in this course, as far as I know, and because I still haven't seen everything that I'm going to do yet. All the examples that follow are ones from Sengel, examples that I thought were useful, and hopefully you will find them useful as well in doing the homework.